Welcome back, everybody. Let's work through this group work on Green's theorem. So this first one has us integrating a line integral here, and we're moving around this curve that we see over in the picture. And so yeah, if we were going to do this the standard line integral way, we would need three line integrals, parameterize this first segment, the vertical segment, and then the last segment. And so we have to translate the line integral for each one of those. And it wouldn't be too terrible. They're just three line segments, but it definitely take a lot of work. And Green's theorem allows us to completely bypass that and just translate this line integral into a double integral over the region D of qx minus py. And so here the region D is the region that this curve bounds, and so we just have to figure out our function that we're integrating and set this up and go through it. Right? And so the stuff next to our dx, that's our p, next to our dy, that's our q. And so our double integral here becomes qx is then going to be, so with respect to x, I guess that is 4xy, just taking the partial of q with respect to x. P with respect to y is going to be 2xy. And so it looks like we're integrating 4xy minus 2xy, which is just 2xy over this region. And so here we need to decide if we want to integrate by setting x moving y, or setting y moving x. And setting y moving x would give us two double integrals, so we definitely want to set x and move y. So y will be our inside, x is our outside. Y is moving from our bottom line here to our top always, and the bottom line here, just looking at our coordinate system, is y equals x, and the top one is going to have slope 2, so y equals 2x. And what x's are we doing this for? Looks like from 0 to 2. Right, at this point, we just compute this double integral like we always have. So it looks like y is our starting variable. If I slide this down to give us a bit of space, so we're going to get what, x, y squared as we antidifferentiate, evaluate from y equals x to 2x, and so we'll get what, x times, plugging in 2x is going to give us 4x squared, minus x times x squared, which is 4x cubed minus x cubed, and so that's going to give us 3x cubed, the value of our inside integral. Now we just need to integrate with respect to x. And so we're going to get 3x to the 4th over 4 as our antiderivative. Evaluate from x equals 0 to 2. And so that's going to give us 3 times 16 over 4 minus 0, and that boils down to 3 times 4, which is 12. Looking at our next one, we have a rather intimidating looking line integral here, where C is this circle that's not even centered at the origin. It's kind of over here, centered at 4, 0, I guess. And radius 3, so it kind of looks like this. So there's our curve. And using Green's theorem means taking this line integral here and swapping it out immediately for a double integral over the inside of this region. Of our qx minus py. And so, looking at q, which is the thing next to our dy, that thing's partial with respect to x. Actually, this gives us 4. And p is partial with respect to y. It's going to give us 3. That cleans up nicely. And at the end of the day, 4 minus 3 is just 1. And so here, we actually don't have to integrate at all, because when we integrate function 1 over a domain, that's just going to hand us the area of that domain. And so here, since we're staring at as a circle as the region we are integrating, just pi r squared is what we need, and our circle has radius 3. So 9 pi is the value of our integral. All right, this next one, we have an area formula here given in terms of a line integral. So if we have a region here and it's a closed curve boundary moving around it, the claim is that the line integral of x dy is going to hand us the area of that region D. And so to prove this using Green's theorem, once again, we can just use Green's theorem to swap out that line integral for a double integral and see what we get. And so Green's theorem says that's going to give us the double integral over D of qx minus py. And here we can see immediately what our q is, but there actually is no dx, you probably noticed, and so we can kind of imagine that there's like a 0 dx floating around, and so our p here is that 0. And so q with respect to x is just going to be 1, and p with respect to y is just 0. And so once again, we end up integrating the constant function 1 over our region D, which will just hand us the area. And so our formula here is true. If we want to compute the area of a region, we can just compute the value of this line integral, which moves us around the outside edge, which is kind of fun. We can put that to work here with this next example. Now we're looking at a cycloid, which is formed by kind of strapping a Sharpie to one point on a circle and then just pushing that circle, letting it roll. And here's the curve that that circle will trace out. If we want to find the area bounded by one arch of the cycloid using our formula, we need to compute the line integral around the outside edge. And we do need to go around all of it, so we will have a portion along the x-axis, and then we'll want to move backwards along the cycloid. So, to compute this line integral, we'll have two pieces. We'll have the x-axis piece of x dy, and then we'll need to add that to our cycloid portion, x dy. In each of these, they follow the standard process for computing line integrals. We want to first parameterize our curve, and then use that parameterization to translate our integral. So let's start with the x-axis. In order to get our parameterization, right, we want to figure out the function that's going to hand us all of the xy points along our x-axis. Well, the x-axis, though, always has y equal to 0, and so we can actually just use x0 as our parameterization. Leave x as x, set y to 0, and then here, to start at the origin, that's starting x at 0, and this point here, where we drop down, that is going to happen at the x value of 2 pi, which we can see here by plugging in this parameter value of 2 pi in for x, and 2 pi minus sine of 2 pi, and so our final x that we're looking at is 2 pi there. And so using that parameterization, we can translate our x-axis integral going from 0 to 2 pi x is just x. Dy, that differential, it becomes y prime dt in general. So for us, our y, though, is 0, and so y prime is just 0, and our parameter is x. So I'll write dx, but we're going to be integrating 0 over the x-axis, and so that's just going to hand us 0. So actually the x-axis integral will contribute nothing to our area computation. It's all going to come from this cycloid piece. Okay, now to get our parameterization for the cycloid, again we want to know our function that's going to hand us the xy points all along the curve. But our xy parameterization is actually handed to us in the statement of the problem. And so our parameterization is t minus sine t, 1 minus cosine t, and t, for us, since we want to move backwards, we actually want to start t at 2 pi and go to 0. Okay. If we do that, then this integral becomes the integral from 2 pi to 0. X is this from our parameterization. So there's t minus sine t. And then dy, once again, becomes y prime dt. Here's our y, and so y prime is going to be positive sine. And so distributing here, we have the integral of t sine t minus sine squared t. And this is what we got to compute. And so here we have these kind of two different pieces. We have the t sine t, and we have the sine squared. Well, how are we going to integrate these? Well, we want to treat these individually. This first one, t sine t, this is a classic integration by parts computation, and sine squared, we want to use an identity to reduce the power. So we're going to treat each one of these individually. First one, second one. And so our first one, using integration by parts, the relevant formula for integration by parts is that the integral of u dv is uv minus the integral of v du. The way that I've heard this phrased is it's ultraviolet minus super voodoo. Ultraviolet minus super voodoo, now you know integration by parts. Anyways, so up here, u is the thing we want to take the derivative of. That's going to be our t, and then the sine t, right? That's playing the role of our dv here. So what we're going to get, feeding in, we're going to get u times v. So as if so u is t, then du is just 1, dt. And if dv is sine dt, then v for us is going to be what? Negative cosine t. And so u times v is going to be negative t cosine t. And since we are computing a definite integral, we'll evaluate that from 2 pi to 0. Subtract the integral from 2 pi to 0. I just realized I wrote that in a crazy way. We want to not integrate, but evaluate. That should be a vertical line. And then we'll integrate v, which is negative cosine. So that negative, I'm going to make that a big plus out front. Cosine t times du, which is just 1 dt. And so here we go. This first one, plugging in 0. We'll get 0 because of the t. Plugging in, we'll get minus the negative. We have 2 pi, and then times cosine of 2 pi, which is 1. And then to that we'll add the value of the second integral, which is going to be sine t evaluated from 2 pi to 0, which gives us, plugging in 0 for t, 0 minus sine of 2 pi is still 0. So it looks like altogether this first integral gives us 2 pi. And the second integral, which we will want to subtract because of the subtraction there, the relevant formula is sine squared t is 1/2 1 minus cosine 2t. And so the integral for sine t is the integral of that thing, and so we can pull out the 1/2 1 minus cosine 2t, and we are going from 2 pi to 0. And so anti-differentiating, we're going to get t minus, we could do a u sub here, we can just do it by hand as well. It's going to have to be 1/2 sine of 2t, evaluating from 2 pi to 0. So if we plug in 0 to this thing, we're going to get 0 minus 0. Subtract what we get when we plug in 2 pi. We get 2 pi minus 1/2 times sine of 4 pi. Sine of 4 pi is 0. So if we look carefully, at the end of the day, we have 1/2 times negative 2 pi, which is negative pi, but we are subtracting that, so all together we're going to get 2 pi minus negative pi, which is 3 pi, which is going to be our final answer because, again, the integral along the x-axis contributed nothing, and so we could think of this 3 pi as 3 pi, plus 0, but 3 pi is the final value that we get, and this is then telling us the area under that cycloid. Great work, everybody. I'll see you next time.